Calculus 2. 5.1 is the section. Area and estimating with finite sums. These are the basics for defining the integral. So, how do we find the area of stuff? Let's first of all, let's take a picture here of a circle whose length is 1, radius is 1, and just use the first quadrant. So the region we're talking about is y equals x squared. I'm sorry. Let's just use x squared, I guess, because we're just going to use a quadratic. My bad. The x-axis and the y-axis are also going to be borders for this. This y equals x squared, it's not quite a circle, so I was going to try to use that as figuring the area. But maybe this is good because it's really hard to figure this area inside this curved and then straight lines for the other sides. But we can do that. We can approximate it by taking, say, one rectangle. If we use a rectangle, I guess this would be a square. A 1 by 1 square is when when this rectangle or square, it's a 1 by 1, right? So the area is equal to 1 times 1, or 1. Well, that's not a very good approximation because it leaves all this extra stuff here. So let's take two rectangles. One of them we'll say is this big, but the other one is going to be a little bit lower. So now it's not so tall. We have, this is 1/2 and this is 1/2. The height for this one is 1, so the area is 1/2 times the 1 for that left rectangle. And then the 1/2 times, well, we need this height. And the height is when we plug in a 1/2 for x, because it's the y value. So if we take 1/2 and square it, we get 1/4. But we know, let's see, that doesn't sound right at all, does it? And that's because this is not the equation for this. It should be, because it's opening down, it should be a negative x squared for one of them. And because it's up 1 unit, it's a negative x squared plus 1. So let me write that over here. It's really 1 minus x squared. So when you put a 1/2 in here, you get 1 minus 1/4, or 3/4. That makes more sense. So this 1/2 width times the 3/4 height. Now this gives us 1/2 plus 3/8. Half is 4/8 and 3/8, so a total of 7/8. I guess that must be getting closer. It's not area 1. It's really not area 7/8 because we still have this extra area sticking out here. Well, you can keep on going and do that with 3. I guess we'll do 3 just to show you. If we use 3 rectangles, what is the area? Well, now, let's see. We have this height, which is still easy to calculate, 1/3 times the 1. But then we have also width of 1/3 here, so it's 1/3 again, times, but now we need the height at 1/3. So if we plug in a 1/3, 1 minus 1/3 squared, 1 minus 1/9, or this is 8/9. And that would go here, 8/9. But now we have another rectangle, 1/3, this last rectangle, and now this height is at 2/3. So we get 1 minus 2/3 squared, which is 1 minus 4/9, which is 5/9. So this is 5/9 here. Let's see. This area is 1/3 plus, and I guess we can do this as 8/27 plus 8/20. No, that's 5. 5/27. And how many 27ths is 1/3? We have to multiply by 9. So this is 9/27. And we get a total of 9 and 8 is 17 and 5 is 22 27ths. But still, that's off because we have stuff sticking out. We have extra. Now we can keep on doing that, and the more rectangles we do, the closer and closer we get to the actual area. Let me just do this look ahead, and what's interesting for integrals here is if we find it's not going to be an indefinite integral, it's going to be a definite. We're going to go from 0 to 1. So we're going to need limits sometimes for this 1 minus x squared function dx. When we go 0 to 1, we evaluate the antiderivative, which is x minus 1/3 x cubed, and we evaluate that from 0 to 1. That gives us, plug in a 1 minus 1/3 of 1 cubed, minus, put in zeros, we just get 0. So what is 1 minus 1/3? Well, we get 2/3. That is the actual area. And if you can look at this, 22/27, we're getting a little closer to 2/3. It would be 20/30. So we got a little too many, a little too much, but it would be getting closer and closer. So let me go to another screen. Now from the last screen, we saw that all of our estimates would be larger. They call that an upper sum. And that's by using the left-hand side here. This is an upper sum. If the estimates are all smaller, until you go to infinity, we'll find that's a lower sum. And if you use the midpoint of that rectangle, it's easiest to see, I guess, with this one right here, that you got a little inside and a little outside, so to speak. And so this is a better sum. This is the midpoint rule. This can also be the left sum. And if you call it the left RAM, the RAM's going to be rectangular approximation method. Should use all capitals, I guess. RAM, not the RAM in the computer or anything. So lots of times they call this LRAM. Using the right side of the interval for your height is RRAM. And using the middle point is MRAM. Now the left side doesn't always give you the upper sum. It's the one that gives you more than you need, which is the upper sum. And the right side is not always going to be the lower sum. But it seems the midpoint's always the midpoint. You'll get the same value no matter what. Now what we'll do is we'll have start talking about Riemann sums. And there's a program that I can make downloadable. I'll have to figure that out a little bit, but it's called Riemann, and you also have to include DR lines when you copy this. But this is a program on the TI-83 or TI-84 which does these LRAMs, RRAMs, MRAMs, and it can be helpful for doing some of this. A pretty good little program. It was really picked up initially off of the internet at the TI website, and then Mr. McGrath and I sort of made it a little better, made it sort of nicer to use in one sense. Theirs are a little bit rough sometimes and doesn't always have a nice interface. Interface is hard to get to sometimes to make it look nice. So eventually we're going to have this RM, MRAM, LRAM stuff and lead up to the Riemann sums in a different section. So how do you use these things? Well, let's go to a new screen and talk about distance traveled. If we do not have the function for velocity v of t, we cannot find an antiderivative that will be for the position. So the antiderivative of this would give us the position. This would be the s of t, really, that we're used to seeing, s of t. If we write the speed of a vehicle at certain intervals, we can estimate this by using the ideas from these rectangles. Therefore, the distance traveled can be figured out because we can figure out the position every once in a while. And go back to our friend, distance traveled, d equals rt. A very simple little formula that we've used an awful lot. Okay. How do we mean this? Well, suppose this is the x and y axis, and we have a height that gives us the velocities, and another height gives us a velocity, another height that gives us a velocity, and another height that gives us a velocity. And this x really is time, so you can call it t if you'd like. It's probably better since we're using time up there. So we're going to use a t, I guess. And this is our function s. No, our function's v. We're taking the antiderivative of. So this is the function v of t. So, okay. If we break these all into the same interval, say 1 second or something like that, this is really the change in time. We can use delta t. But if it's all the same, it'll be sort of nice to keep it that way. We can go from the left, we can call that starting point A, and the right we can call ending point B. And if we make this 1 second, then delta t would equal 1. Well, if our velocity function, v of t, is 160, and we'll use 9.8 for the metric system, 9.8t. We'll say that we're in the metric system, this velocity we know. So the initial velocity, v of 0, plug in a 0 for t, you get 160. V of 1, you get 150.2. I have to put that in your calculator. V of 2, you get 140.4. V of 3, you get 130.6. So that's these, the V of 0, V of 1, V2, V3. So if we make, try to figure out the area under this curve. The area under the curve will be the position function and give us distance. We know that we have these rectangles. We'll use 1 second and then the 160 and then the 1 second and the 150.2 and then the 1 second and the 140.4 and the 1 second and the 130.6. Hard to fit that 140.4 in there. We can figure out all that stuff because we just have to add those up. When you add them up, you get a total of 450.6. Now what's important here, and I guess I didn't mention, this 130.6 is, if we, let's see, how do I want to say this? If we're using just these three for the area, that V3 is really not included in this situation. So maybe I should just scroll that out. Because it is from 0 to 1, and then 1 to 2, and 2 to 3. So the V3 is the height over here. But it's going to be shorter than that 140.4. If you add the 160, 150.2, and 140.4, that's where we get the 450.6. This is the LRAM. Suppose we want to do the RRAM. Well, now we don't use the left side, the 160, but we do use the 150, the 140, and the 130.6, because that's using the right sides of these rectangles. And that gives us, if we add them all together, 421.2. Okay, so this is a little bit too high, this is a little bit too low. What should it be? Well, MRAM gives us a better approximation by using the midpoints. Well, that means we have to find the midpoints of this stuff. So we don't want V of 0, we want V of 0.5, and V of 1.5, and V of 2.5. And if you put that in, you get 155.1 and 145.3. Let me put it up here. And 135.5. 35.5. If you add those up, you get, for the MRAM, 435.9. Now this makes sense if you look at it this way. MRAM is really the average of the LRAM and the RRAM, if we use the same number of intervals. So if you take 450.6 and add 421.2, you get 8, let's see, 1, 7, and then 8, right? If you divide that by 2, you get 4, 3, and then because it'll be 11, it'll be 5, and then 18 will be 9. 435.9. So if you can find the LRAM and RRAM, then you should be able to find the MRAM, which is the best approximation really for any of these. There are situations where using LRAM and RRAM can be exactly right if the curve is not really a curve. So you can use the Riemann program. Let me bring that up and show you how it works. Okay, so I guess I just hit the screen here. Let me bring this back up and show you this program. This is a TI-83 Plus, but to me it works a lot better than some of the newer stuff as far as this emulator is concerned. I can go into programs and still get programs that work on the TI-84. This Riemann, when you run that, LRAM, MRAM, RRAM by Riemann. Ma'am. Anyway, setup. If you go to the setup, you can enter the function. So I want to define the function, number 4. no quotes. So I want that 1 minus x squared. Okay. Now it shows you this again. I want to go from 0 to 1. So I want to redefine b, number 2, so it's just a 1. So 1 minus x squared, 0 to 1, and I want, I guess, 3 intervals. So I need to define the n, which is number 3. So that's what I want. That's the setup. We can then return, which is number 6. I guess we can find the area too. So 5, find the area. It finds it all 3 ways. Oh my goodness, it's because I made the function wrong. And that just goes to show you, you need to know a little about your function in order to make sure you don't make a simple mistake. Setup. Because I don't even know what this function is. And that's one of the problems. It is not the 1 minus x squared. If you were given these values and not told what the function is, you could still get an approximation. But we know what it is. It's this one up here. So let me change that. We're going to change the function number 4 to 160 minus 9.8 t, but we're going to use x because they're going to use y also. Sorry, it's the way the program was written. It's not bad. Now we can find the area, number 5, and there it is. And I'm glad this happened too. So you should be able to look at this and say, well, that's not right either. This looks like some of the area that we talked about, but those aren't even right. It's because I was going from 0 to 1 for that other function. I need to go from 0 to 3. So this is good to set up. If you don't have it right, I want 0 to 3 and then 3 separations there. So I want to define b as 3. That's number 2. Make that a 3. Okay, now I think I've got it set up right. Find the area. There it is, 450.6, 420. Then maybe that's a good, you need to play with this a little bit to get used to it, to make sure that you have everything set up correctly. But I got these answers too. Let me go and the find area stuff. If you go to that 2, there are 3 ways. That's the same thing we did. If you go to 3, which is draw, this is what's sort of nice. You can do it for the left point, the midpoint, the right point. You can use trapezoids and it'll draw this for you. It was pretty slick the way they did this, and we just had to clean it up a little bit, but it works really nice. Left, if we do the left, number 1, there's the curve. And you can see it's a little bit too high. When you press enter, it gives you the approximation. If you do the right, now you can see it's a little bit short because it's got this extra inside. And that is the 421.2. And you can do the midpoint, which is interesting because the way they calculate this, notice the midpoint a little bit inside, a little bit outside. The best approximation for things like this, 435.9. You can use trapezoids, and it just averages the left and the right, which is the same as the midpoint in this case. That's the left. This is the right. And when you average them, you get what I got. Anyway, return is number 5. And then quit is number 4. So you can use the calculator to help you with things like this. It can help you catch some errors. If I would have done it wrong, it would have caught some errors, forced me to look back at this and see where I made the mistake. So, one last thing. They talk about error magnitude. It's the true value minus the calculated value. The error magnitude. And the error percentage is the error magnitude. Makes sense. What do you divide by? You can't divide by 100. You divide by the true value. So if you want to, you can think of the percent error as true minus calc over true. One way to think of it. So if we wanted the true error here, we can find the integral from 0 to 3 of 160 minus 9.8t dt, which gives me the function 160t minus, well, we add 1 and then divide by the new thing. So it's the 9.8 over the 2, which is times t squared, evaluated from 0 to 3. This just gives you a preview of what we'll be doing later on. So you plug in the top number, 160 times 3 minus 9.8 over 2 times 3 squared. And that number you subtract, plugging in a 0. But 0 will give us a 0 for both of these. So, what is 3 times 160? Let's see, 0, 18, 480. What is half of 9.8? Let's see, it's a 4.9 times 9, because this will be a 3 squared. So it's 81, 36, 44, 44.1. Does that make sense? 36 and 8.1. Yes, okay. That should be correct, minus the 44.1. So 480 minus 44.1 is 0.9. 9 minus 4 is 5. 3, 435.9. Oh my gosh. So, what did I get on that last one? It was 435.9. So if I take the true and subtract the calculated, the true is the 435.9, the calculated is the 435.9, and divide by 435.9, I get 0 over 435.9. There is 0% error for this. That doesn't happen as much as you'd like, I guess. But it shows you, I guess, how you can find that. Use one of your LRAM, RRAMs, MRAMs to calculate the calculated value. You might have to use integral calculus to get the value of this thing, which we haven't talked about yet. But they'll give you something, I guess, where you can figure things out without using an integral. Anyway, that's section 5.1. Let me make sure I don't have anything else to say. Oh, yeah, I do. Just a second. Next screen. So let's continue. Got a couple more topics here. Displacement and distance traveled. What is the difference? Displacement is how far you are from where you started. But that doesn't take into account that you might have moved backwards or done some crazy stuff in between. All that is the distance, the final distance, subtract the initial distance. And these position functions, remember this is s of t equals, and we'll do it, I guess, the initial distance v sub naught t and 1/2 at squared. So it doesn't matter which units you're in, it's going to be this. That's that s they're talking about here. It's not a 5, it's an s. It doesn't take into account any backwards travel. So the total distance, like totally, you have to take the absolute value of t1, v of t1, times the delta t, that's the time during this velocity. This is distance equals rate times time again. And then add to that the distance, the rate here is v of t2 times the delta t. And then you might have a t3 and a t4 and a t5, or you just go up to vt sub n times delta t. So you could have a lot of adding these up. And it's just the velocity at that time times the rate. Rate times time, rather. The velocity is the rate at times this time, delta t. Delta t is almost always the same. And maybe we can mention that here. Delta t is the final, which is usually b for us, minus the initial divided by n. Just divide that distance into n different rectangles. So if you need to, you can use that for your homework. How about the average value of a non-negative function? Let me change the colors here. The average value of a non-negative function. Now, if you have a rectangle, you don't need to worry about the average value. But this is the b and this is the a, so it's b minus a, if you need that. And that length, the average value of the function, is the height here, right? You can call that c if you'd like. So since the function really is a constant value up here, you just have to take that b minus a, or the area, and divide it by b minus a, because that will give you this height, which is the average value of the function. But suppose your function isn't nice like that. Suppose your function does something crazy. Then there's a line here that will be the average value of that function. Some's too high, some's too low. Does that make sense? Now, we can figure out, using a finite sum, the area underneath this curve, and that can act as the area A. And then if this is B and this is A over here, then we can divide by B minus A, and that will give the average value of the function. So we're using the same idea as if this were just a rectangle again, but now it's a horizontal rectangle. For example, let's go to another screen. Number 18, page 260. They give us the function f of t as 1 minus cosine in parentheses. This is pi t over 4, but that's to the 4th power. So how you're going to figure this out? First thing you do, use finite sums to approximate the area. They want this from 0 to 4. So I'm going to help myself with this calculator and put it up here. Because if we need a table, because we don't know how to find the antiderivative. We do, but we're going to say we don't. But you can use these finite sums to help you to approximate it. Okay, we can set up our table. First, we need our function. This is 1 minus cosine pi, and we got to use x, divided by 4, close the argument, close the parentheses for the cosine, to the 4th power. First of all, put that in. Now we have to set up our table, because if we go to the table right now, it'll start at 1 and go by halves. Well, how did it know to do that? Because of how the table was set. So we're going to go second table set. We don't want to start at 1 according to this. We want to start at 0. And do they tell us in this? Maybe they don't. We're going to use 4 intervals. But because we're going to use the midpoint to get a better approximation, from 0 to 4, let's do a couple things here. All this is set up right now except for the table set, and we will want 1/2 eventually here. So put in 0.5 and I'll show you why. Once you've done that, we've got this function. If you set up your window and go from 0 to 4, and we're going to count by ones, that's what the scale is, to figure out your y min and y max and stuff like that, you need to go to zoom and then go down and find zoom fit. It should be 0. And zoom fit will calculate the maximum and minimum y values for the window. So this is what it'll look like after you get it. So now we can take a look at this, and you can see what this thing might look like. The window goes from 0 to 1, scale being 5. It doesn't set up a scale, so let's set the scale up as, I don't know, 1/2, because it just goes from 0 to 1. So now when you graph it, you've got this mark here for 1/2. But this goes 0 to 1, or 0 to 4, count by ones. So that's the window it came up with. Don't worry about the resolution and stuff. You can look that up too if you'd like to know more. Okay, so what if we would like to break this into 4 pieces? If you do an LRAM or an RRAM, these first ones are going to lose a lot or gain a lot from the steep part here. So I'm going to use the MRAM, use the middle. And that's why in the table set, I said go by 0.5, because for my picture, I'm going to use 0.5, 1.5, 2.5, and 3.5 for my calculations. So I need those values from the table. So when you go to the table, don't use 0. You use the 0.5, 1.5, 2.5, and then go down to the 3.5. Yours might all show if you've got a TI-84 with a better screen than I do. I guess I can go down 1 though, can't I? So these 0.5s are what we want. Write those down. Now when I click on this screen to write it down, I'm going to lose that, but I've already got it written down. You should be able to get to that. They are 0.5, 1.5, 2.5, and 3.5. And what is the Y value? Well, if you read that off there, a little hard to read now, 0.271. 3 places is probably okay. 978. Oh, yeah. Once again, 978. So you know it's symmetric, or should be. And 0.271. So that is now, because now we know what this thing looks like. It does something like this. And here's 1, 2, 3, and 4. So we got this point that we're drawing our rectangle. This point, drawing the rectangle. This point should be the same, but it's not. And this point. So we've got some in and some out. But it should be a decent approximation. If you add up these 4, you get 2.5. Now that is the sum of all these heights, but now you've got to take and divide that by 4. Which gives us the 0.625. And that is the average value of the function. And this is one of those situations where if you look and just say, it sort of makes sense. I got a low of 2.5, almost 3, and a high of 10. What's in between 3 and 10? Well, 6 is pretty good. 3, 4, 5, 6, 7, 8, 9, 10, so 3 1/4. Looks like it might be right. Does this make sense? And of course, you can draw this thing. Now, let's also, because we'd like to see if our 2.5 makes sense, if we run the program, second quit, program, boy, I've got too many on here. Oh, come on. I went right past it. Remon, run it. Now I'm going to need this function. One minus, put a parenthesis, cosine pi x divided by 4, close the argument. See, I'm trying to do that before I even can. Define the function 4. Let's try this again. 1 minus the cosine, shows me I should look up, pi x divided by 4, close that to the 4th. Oh, guess what? I'm glad this happened too. I need to know that this is not just that argument of the 4th. So to insert something, second delete, the insert is above that, and it should give you second insert. Now I got to insert the cosine also. Left parenthesis cosine. You'll see the cursor change into an underscore instead of a box. Then you know you're in insert mode and things will get pushed to the right. Now we need a parenthesis to the 4th. So this whole thing here with the cosine is to the 4th. Let's see here. That should be done. So we need to set up a is 0. Maybe a little slower in your calculator too. Why didn't it put that? Number 1. A equals 0. Did it leave that 4 there? We'll see. I need B to be 4. Oh my goodness. I need setup. B is 2. It's got to be 4. And N is 4. Why is it giving me that 40 for A? Let's see what happens. Find the area. 2.5, 2.5, 2.5. That's interesting. That's the 2.5 approximation. I don't know why it says 40 for A. I hope yours doesn't say that. Anyway, that's one way you can check your work to see if this... So you approximate the area. Let me get rid of this. You then divide by B minus A, and that's the average value. The area divided by the length. Okay, maybe that's enough. I sort of stumbled around there. But I don't have any more examples written down for you. If you need some, give me a call. I'll see if I can confuse you even more and see how you can do this. See you next video.